Well, good afternoon. Thank you for coming. I'm going to do a little bit of an apology first. This is a brand new talk. I haven't presented this material previously, so it could end up being really, really terrible, but hopefully you'll learn a little bit, and some of it's got some of my mistakes in there, so hopefully you'll learn from those too. So today I want to talk a lot about software performance, but this is not going to be one of those talks where I'm delving down into hardware details and talking about mechanical sympathy and those sorts of things. While those things are incredibly important, what I want to talk about today is more sort of a higher level concept, sort of design concepts. How you approach difficult problems when you're faced with them. You get given a fairly interesting set of challenging performance requirements. How do you even start? How do you make decisions about what you really want to achieve? And I've been working at LMAX, this financial services company here, for about 6 years now. And we have a whole bunch of really interesting and challenging performance requirements. So we're talking about sort of sub-second, sub-millisecond latencies. We do a throughput sort of in the tens of thousands of transactions per second. And working in that sort of environment for a fair amount of time has changed my approach to development a lot. I think I've certainly gotten a lot better. And through that change, I've sort of developed a bunch of principles that I generally apply when writing software. They're great for trying to write fast software, but I think they're generally applicable as well. And the basic principles are, 1, solve the problem. This might seem almost ridiculously obvious, but I think back to the sort of developer I was maybe 8 or 9 years ago. I used to be a consultant, and I'll waltz into a customer engagement, and I'll open my toolbox, and out with the JVM, and out with JBoss, and out with Spring, and out with Hibernate, and then go, oh, sorry, what were you wanting me to do again? And I'm already stepping forward and making a whole bunch of architecture decisions, design decisions, product choices, without really sitting down and understanding the problem. And I see this time and time again, people making technical and design decisions for other reasons. A common one I've seen, and certainly one I've probably made the mistake of in the past, is going, that's an interesting problem. I know, I'll write a framework. That type of thing. Second is understand the trade-offs. Whenever you're going to be building anything, you're going to be making a whole host of decisions about operating systems, virtual machines, programming languages, databases, frameworks, libraries, all that sort of thing. And I know we all have sort of our favorite ones, the ones we like to use and the ones we're familiar with. But you can't really truly understand a piece of technology without understanding what trade-offs it's had to make. No piece of technology is perfect. And without understanding those trade-offs, you can't make an informed decision about whether that thing is going to be right for the problem you're trying to solve. And that leads into the final one, number 3, make informed decisions. So this is about when you're faced with a fairly challenging problem, you're obviously at the beginning of any sort of project or any sort of product life cycle is the point where you know the least. So what you have to do is move very rapidly to a point where you understand the problem better. And this is a lot about being reasonably scientific with how you approach your problem solving. Thinking about hypotheses about how fast does this thing need to run, or what functionality does it expose, and then designing experiments in the forms of tests and performance tests to tell you whether that piece of software meets those hypotheses. So I've used this term performance a couple of times now, and it's kind of a vague and amorphous term. It really is sort of an aggregation of a whole bunch of characteristics around software. So I'd like to dig into what those specific characteristics are. First off, throughput. This is the one that people typically think about when they think about performance. This is just largely the volume of work that your software is capable of doing. Often you'll measure these sorts of things in things like transactions per second, or messages per second, or operations per second. And to use a road analogy, which I'm going to use a couple of times, it's sort of the number of cars per hour that can traverse a road. The second one, and this is the one that's really important to us, we talk a lot about latency where I work, and this is simply the time it takes for an individual transaction to go from start to finish. I've often seen people make the mistake of trying to use mathematics to correlate latency and throughput. I've seen many places on reputable blogs and article sites, people say that latency is 1 over your throughput, or your reciprocal of your throughput. But that math is really bad and tends to break down when you get any sort of complexity in your software, especially if you introduce things like parallelism or pipelining, it breaks down. So latency is something that should be measured and understood independently. And when you're talking about the latency of a system, you're never really talking about a single value. You're talking about a distribution of a large number of values. And so when you're talking about latency, you'll be saying something like, what is the 99th percentile latency? What is the 49th percentile latency? And also it's worth remembering that these distributions of latencies are never normally distributed. So if you're using terms like standard deviation to describe the latency of your system, you're misrepresenting completely what it's doing. Two, this one, scalability. This is one that people often talk about a lot. You see a lot of people mentioning this, talking about things like web scale and MongoDB and all that sort of thing. But scalability is simply how well does your throughput increase as you increase the capacity of your system. If I add another server, do I get another server's worth of transactions per second? Going back to that road analogy, we can simply add another lane to the road to increase the throughput, but we wouldn't necessarily get any sort of increase in latency. And the last one I want to mention, and one that's becoming more important nowadays, is power. So this has come about much more because of the advances in mobile devices, your tablets and your smartphones. But if you've got a poorly designed application or poorly optimized application, it's going to chew up more battery life more quickly, leading to a poor experience for users. And the other place where power turns up a lot is the opposite end of the spectrum. So you're talking about the big data center guys like the Googles and Facebooks can make significant cost savings when they're optimizing for efficiency, just simply saving on those power bills. And the interesting thing about these characteristics and why they're important to mention is often you'll be trading one off against the other. So for example, we care a lot about latency, and we trade off power significantly in order to achieve it. The way that we do this is through the very high performance or the very low latency path through our system. We don't have a single lock. And we get around this by having all of our threads busy spin. And this gives us a really nice low latency profile because we don't pay a lot of lock contention costs. But our main Exchange server will sit running at 700% CPU when it's idle. And that's just a core trade-off we make. As our head of operations likes to say, we run them with the flames shooting at the back. So those are those key characteristics. Now I want us to talk a little bit about the case study. So I'm going to talk, when I talk about these design concepts, a piece of software I worked on, it was about a year or so ago. I'm going to try and sort of break down some of the decisions I made through that piece of software and try and explain some of the thought processes that I run through. And there's two main areas they're going to look at. One is data storage, because this is quite often the biggest bottleneck in just about any system that you're going to work on. It's probably one of the most important designs, or the most important design decisions you'll be making will be around your data storage. And two, how to create a nice responsive UI and give a great user experience for our customers or for our users. So this is the main screen of the piece of software I want to talk about. So in the financial exchange world, which we're in, we run an exchange where we have large numbers of customers, large banks, big hedge funds. They send us their orders. They come into our exchange, and we look for orders where the prices match. We match them together, and we execute trades between those parties. In any sort of electronic exchange, there's a regulatory requirement for you to run what's called an orderly market. And this is basically, it's the responsibility of the exchange to make sure nothing bad is going on. And things that are bad include stuff like insider trading, prearranged trades, which could be an indication of money laundering, or algorithms that people are running to try and trick other participants into the exchange into making bad trades. To do this, we have a special team set aside we call market operations. And that becomes their responsibility. And one of the key tools that we give them, we call a surveillance system. And that's what this is. So a surveillance system sits downstream of our exchange, takes a feed of events, and can rebuild the state of the exchange such that they can inspect it and understand it. They've got things like, they've got this big chart of what's been happening over the last sort of period of time. They get real-time updates to the prices. They can look at individual orders and trades and see who made them at what time and what prices and what quantities. But also they can go back to arbitrary points in time, focus in on a single order, and then single step their way through the market, a little bit like a debugger for a financial exchange. So this is a little bit of an architecture of where this fits in. I've broken this up into sort of two areas. The bit at the top is our existing exchange, and I've sort of put a ring around it and said sort of latency sensitive. That's the key performance requirement for that part of the system. And that consists of sort of our customers. They come in and connect to a gateway, and they send messages to our gateway. The gateway transforms those messages into a nice type binary format and sends it to the exchange system, which does all the necessary work. Now, I've put a couple of numbers on there. These are numbers that we benchmark at the moment, or have done sort of a few months ago. We've upped these a little bit recently. We have kind of an interesting quirk in the way our system works, that we'll get about 10,000 transactions per second in, but that will result in something like 160,000 messages per second out. And this is because an individual order may have about 3 or 4 response messages to an input message. But also, those inbound messages are allowed to be batches of orders. So it could be containing up to 12 individual orders. So once you sort of multiply that up, you could see about 30 or 40 outbound events for a single inbound event. Bit of sort of statistics from production, and it's somewhere between, the fan-out rate is something like 1 to 16. So you imagine these systems that are running downstream of the exchange have to be able to deal with a fair amount of throughput. The other interesting quirk with this exchange is that that delivery of messages has to be guaranteed and durable. Every single one of those messages has to make it down to those downstream systems. To make that work reliably, the exchange will actually maintain a fairly large window of the messages that it has sent. So if any of the downstream systems happen to miss a message, which is quite possible because we run over UDP multicast rather than TCP, and if there's some sort of delay in, for example, a surveillance system, it will have to request a redelivery of those events. And that's very expensive, and that can cause significant latency spikes inside the exchange. So that's the key thing we've got to protect against. These downstream systems, like our surveillance tool, has to be able to deal with that throughput, but deal with that throughput in a sustained manner. So anything like a large garbage collection pause, and by large for us I would say something in the region of 1 to 200 milliseconds, is sufficiently large to cause problems for the upstream systems. And so that 160,000 messages per second, that's the thing we have to store and index and retrieve from. So we need to come up with some mechanism for storing that. So we have MySQL as the main database we use for a bunch of things, but fortunately we don't use it for everything, certainly not the high performance parts. And due to other parts of our system, we've pushed it largely to where its limits are, so we've got a fairly good understanding of how it behaves. And certainly 160,000 is way beyond what MySQL could handle, given the hardware we had available. So we needed some sort of alternative. And the best way, in my mind, to look at an alternative is to start digging into the data itself. So admittedly, we don't use SQL, but I've represented our main query here using SQL, just to give you a bit of an understanding. But what's really interesting is this is the only query that matters. So all of a sudden, I've got an interesting simplification, and I can use this information to try and find a solution that's simpler and potentially faster. So basically, I'm selecting a whole bunch of data. The first constraint I'm applying is an entity ID. Now, for us, that is what we would call a market. So inside of an exchange, most exchanges will run multiple markets. So for us, that's varying different foreign exchange crosses, like euro to USD is one market, Australian dollar to Kiwi dollar is another market. And these markets don't talk to each other. There's no cross-talk between these things. The messages relating to them are completely independent, such that our operations guys aren't looking across markets. They're only ever looking at one at a time. So that's the first constraint. The second constraint is timestamp. This is essentially time series data. We're just saying, I've got a start timestamp and an end timestamp, and I just want all the events in between in that time order. So because that's my only query vector, I only need a single primary key. There's no sort of secondary indexing required. I can build a nice compound key out of the entity ID and the timestamp, and that's sufficient. What's probably not readily apparent here is the data is also just a blob of bytes. We've got higher level constructs in our Java code to convert those bytes into objects and do useful things with them. So I don't need any sort of structure. So one of the obvious possible choices for this is a key value store. And we started looking around for a bunch of them and decided to pick LevelDB, which is a Google product. It's a really interesting piece of software. It's what's known as a log-structured database. It takes in data, and the first thing it does with a piece of input data is it just writes it down to a sequential journal. So that's really good, nice, efficient insert performance. But then what it will do, because it's potentially receiving events in arbitrary order, it needs to index them. Because while the events are still sitting in the journal, it's got to do linear scans through that journal to find data. So what it will do periodically is it will compact up that journal file. It will scan it up and build up a level above the journal file where it will sort of look at things like inserts and updates and coalesce that into a single object and inserts and deletes and throw that data away, and then reorder it by the keys. But once it's built up to those levels, we've now got the data that's indexed. You're doing sort of a tree walk to find data. But also the data is organized according to the keys. So our traversals, that sort of traversal by timestamp, is also nice and efficient. So I did a micro benchmark using LevelDB, and I chucked it into the system. And the micro benchmark indicated to me that it was going to be all right. I was able to keep up with the sorts of volumes we needed. And here is where I made my mistake. I didn't do enough experimentation. My experiment wasn't really sufficient to prove whether it was going to be good enough or not. So I then went off and did all of the work necessary to get all the functionality working for integrating LevelDB into our system. And I burned a couple of additional iterations doing this. Whereas what I should have done is just written enough for the writes to be going into LevelDB, such that I could take the software, put it into our big macro performance testing environment, and ensure that it worked end to end. When I finally got it into the system, it would run for about 5 or 10 minutes, then it would start to stall. Queues would fill up all the way back to the networking thread, the network buffers would fill up, we'd get packet loss, and we'd start getting those horrible redelivery requests I mentioned earlier, creating nasty latency spikes in our exchange, which simply weren't acceptable. And the reason this occurs is LevelDB's compaction process blocks the writing thread, which is the thing that we really didn't want. And so I tried a number of different tuning options. I tried a number of different forks of LevelDB in order to see if I could get around this. But fundamentally, I couldn't get past the fact that it was blocking the writing thread when it was doing this compaction work, and this was leading to these delays. So unfortunately, it had to go. So this is where I had to sort of take a bit of a step back and go back to the problem and try and understand again, are there any other characteristics of the problem I'm trying to solve that I could exploit to try and build something that was faster? And there was one. There was an interesting one. Our exchange, that flow of events coming out of our exchange, it has an interesting property in that every single one of those events must be emitted in time series order, deterministically, because a number of other systems in our environment and also the messages going back to our customers, they need to have them in time series order. And that's exactly the same order that I want to index and query them. So the second solution I used was to make use of that feature and store the data sequentially. I didn't need to reorganize it, which was the thing that LevelDB was doing that was causing me the problems. So all I did is I created a set of journal files. Every one of the inbound messages gets simply appended directly to the journal. Unfortunately, the messages themselves are of variable length, so you can't do any sort of random accesses on the messages themselves, which means you can't do any sort of binary search directly. So what I did then is create a whole bunch of secondary index files, one sort of set of files per entity ID. And those were able to contain a very small but fixed length record, which contained references back to the location of the messages in the journal, but also the meta information I needed, like the timestamp. So that way, my inserts were very fast. They were just straight journal appends to the journal and straight appends to the index files. But also my queries were simply just go to the particular set of files for the entity I'm interested in, do a binary chop my way through to find the timestamp I'm interested in, and then traverse the link over to the journal to find the message. And then you can just traverse sequentially through the index file and in sort of roughly forward manner through the journal to replay the events. And all of that ends up being very efficient. You're moving sequentially, you're not doing any sort of copying and moving of data on the insert either. And that ended up working really well. And it ended up being about an order of magnitude faster than LevelDB and didn't exhibit the same sorts of stalling issues that we had run into. But again, it was just a case of paring back and understanding the problem and trying to find a solution that fit. It does mean that I end up with something that's very specific to the problem, but I also end up with something that's very simple. So I want to move on to the next bit now, which is UI responsiveness. So I'm going to bring back up that chart, the picture I showed earlier. And so the really interesting and challenging part of this user interface is actually the chart there, trying to grab all that data. This particular piece of software was actually replacing an existing piece of software. And the reason we were replacing it was this off-the-shelf implementation simply wasn't fast enough for what we were doing. That big flow of events, it was choking on it. During our very busy periods of time, it was getting 20 to 30 minutes behind. But the other problem that it exhibited was in the user interface. They wanted to make the UI reasonably responsive. But the way they did that is said, I know, I'm going to work totally off local data. So when you brought up the UI, it would download an enormous amount of data up front, and, so that it was able to run locally. But unfortunately, doing that initial download of data could take many minutes. So when they brought the system up, you'd be sitting there waiting with the thing spinning, going round and round and round, without actually having any idea of what sort of progress is being made. And that led to a very terrible experience for our users. So we decided we didn't want to do that. We had to do something a little bit different. We had to make sure that when we brought the user interface up, all the data was really available, and then as they were interacting with it, it was able to keep up as well. So the interesting question is how do we tackle that? Well, if you look at that chart, this allows the user to have multiple different zoom levels. They can zoom in, they could zoom out. And they could be looking at something like maybe an hour's worth of data. And thinking about the sorts of volumes that we were running at, that sort of 10,000 transactions per second, per market, you could be looking at a few hundreds of events per second. Now an hour, 3,600 seconds, and a few hundred events per second, you could be looking at somewhere in the millions of events to render that chart if you implemented this naively. And obviously that's not going to work particularly well. Trying to ship 3 million events in JSON over to the browser and render it, it's not going to be great. So one of the things we did is we added as a first-class function of the data store was the ability for the user interface to pass up some sort of bucketing time. So the UI was able to make a really smart decision about, okay, I know how wide my screen is. I've got maybe, in this case, about 1,600 pixels. There's going to be absolutely no need for me to try and render 1,000 data points per pixel. I'm only going to need roughly that sort of number. Maybe 2,000 might be a good amount. So it can then decide, well, if I bucket by some particular time period, and let's say, in the case of this one, maybe I only want one event every 3 seconds, then I'm only going to get maybe about 2,000 or 3,000 events that I need to render. And that's going to be much more efficient in terms of data transfer across the network, and certainly going to be more efficient in terms of memory usage in the user interface and computation time and rendering time. So that's what we did. When we send messages back over to the back end, it simply is able to take that bucketing time, and as it runs through the events, it actually buckets them up and sends much more condensed data back out to the user interface. But that was still not quite enough. So we wanted to look at some other sort of properties of, in this case, the browser. How could we use the way that the browser works to try and improve the throughput, try and increase this responsiveness? And one of the interesting things about modern browsers now is that they can actually issue multiple requests back to the calling server in parallel. I think when I first started doing web stuff with IE6, it was 2, and I believe Chrome, it's up to about 6 or 7, something like that now. I can't remember exactly how many. But we thought to exploit that, what we did is we started breaking the chart up into chunks. So what we do is, if you imagine something like an hour's worth of data, we'll actually break that up into maybe 12 5-minute chunks so that we can actually issue these requests in parallel. And so we get about 6 or so running in parallel. They go all the way through to the back end. That data store is a nice lock-free concurrent structure. It's perfectly scaling to any number of threads that we like. So we're able to increase the throughput that way, and that also helped to make this user interface significantly more responsive. But there's one other interesting behavior here, and if anybody was here during Kelsey's talk earlier, they may have spotted it, is the data's immutable. The data never changes. It's time series data. Once something's happened in the past, it's absolutely never going to happen again, or never going to be changed again. So we're just basically doing this, using this purely append-only model for storing our data. So that when we go and fetch it, we send back to the back end. We send back a URL, a GET request that has the entity ID, the start and end timestamp, and the bucketing factor. And the back end will will receive that, and it will traverse again through its events. But what it will do is it will always check to see if there's an event directly after that end timestamp. And if it is, it can mark that whole block as being completely immutable. And so when we start sending these blocks back up to the web server can go, I see that that particular block is immutable. What I'm going to do is then set the appropriate HTTP cache header. So when the JSON request gets back to the browser starts caching all of this data itself. So what we're trying to aim for is a situation where we're getting to the point where we have the same sort of behavior that the old system did with a lot of data running out of the local repository. But we want to try and get there lazily. We don't want this big delay in getting all the data downloaded. We'll grab what we can when we need it from the server and then slowly build up a repository locally. So as the person's using the user interface over time, because they tend to be focusing on particular areas, we have a very strong recency bias, so they're most often looking at the most recent data, that most of the time they're actually just hitting the local cache, and it significantly reduced the number of requests we're having to send through to the back end. But this is a really interesting model in itself, this whole idea of immutable data and append-only models. And we've actually started taking this and applying it to lots of other places where we hadn't previously. And one of the examples is something like your customer information data. So if you were to imagine you're on a new project, you get your initial feature requests. It's like, we've got customers, they have username, they have names, and they have addresses, and they have email addresses and phone numbers and that sort of thing. And we need to store those. So typically, certainly what we did initially in our first pass of this a few years back is we would take that, we'd build our database structure, we'd write the various operations on top, and we'd have inserts, and we would have updates for when they change any one of those values, and deletes for when they wanted their customer details deleted. And obviously all the appropriate queries. And then what's interesting is the very next set of requirements you get is, well, we need to audit all of that. So every single time that there's going to be a change to that data, we need to write a secondary audit record. And so the interesting space saving that you made by implementing things like modifications to the customer, by having it in place and keeping the data fairly concise, has been completely wiped away by the fact you have to write an audit record for every single change that you're going to be making to your data. And sort of once you realize that there's no efficiency or space win from doing updates, get rid of them. Get rid of deletes as well. Just do appends. And then you can add another couple of nice features, like whenever you create a new row, so you just take the data, you copy it, and update the appropriate parts. You include things like the principal of the person who made the change, the reason for the change, and some sort of created timestamp. And then you very naturally get audit already built into your data model. So you have some of these nice features that it becomes more amenable to caching. You get some of the nice audit features crop up. But actually, so this approach of modeling everything as append-only is something we're actually trying to apply almost across the board. And certainly whenever we're attacking any sort of data model now, we're always starting with, can we model this as an append-only thing? And only if we absolutely cannot do that do we go with the full create, update, delete. So that sort of brings me to the end of the stuff I want to talk about today. Hopefully you managed to learn something. Hopefully some of the sort of design decisions have helped you in some of your systems. And any questions?
Go ahead.
There's a mic coming.
For the performance, do you consider pre-calculating some of the data? So as soon as it's sort of finished the timestamp, you made the calculations of bucketing them already?
We haven't done, mainly because we've got, one of the really interesting things about the data we deal with, and one of the interesting aspects of financial exchanges that differ a lot from a lot of other problems, is we have this enormous write bias to our operations, and nearly 99% of the work we do is writes, whereas most other systems tend to be mostly reads. So we're always trying to optimize for the cheapest possible write operation, and if I can trade that off against a slightly slower read operation, I will. So I wouldn't want to pay any additional cost to do that bucketing on the fly. But also, because we've got caching in place, because we use that sort of immutable data to cache things, is if we felt we needed it, one of the features of the user interface is that it's not a big scale-out system. We've only got maybe 10 or 15 users of this thing. But if that started to grow, what we could do is put a reverse proxy in front of it. So because it's already got the cache header set correctly, over time, that reverse proxy is actually going to build up that set of computed values. Because the request we send back, what we do is we actually have about sort of 10 bucketing levels. So that way, the user interface is always sort of going to highly likely pick a URL that's been used before. And over time, you'll actually build up a cache of those things. So while we wouldn't pre-compute it, by nature of the caching, we almost get that sort of a lazily evaluation and reserve it that way.
Hi, so you mentioned regarding latency, it's a range of values and it's typically not a normal distribution. What sort of distribution is it typically?
It doesn't fit any pattern. I think best described as multimodal. So most statistical distributions will have a lump somewhere, like a Poisson will go out to a side and normal have it in the middle, and there's all sorts of different ones. Ignore all of them when you're talking about latency. Just completely ignore all of them. Look at a tool, something like HDR histogram, which will allow you to plot all that data and then focus strictly on percentiles. That's about the only useful metric you can pull out. So means sort of useful-ish, but worth avoiding. But certainly percentiles, maxes, modes, those are the sorts of things that you want to describe them. But yeah, there's certainly any tool that gathers up statistical information will be okay to use, just avoid using the statistical analysis type operations that you might have sort of picked up in stats at university.
I'm wondering if we've got any advice on how to model append-only data?
So the way that we're doing it at the moment, obviously with time series data, it's obvious. Time series is your key, and so it naturally falls out. For something like our customer profile stuff, which we started converting over to this append model, we just use the idea of putting a version number on everything. And so you then just build in the additional sub-select to say, I want this thing where this thing's version number is the highest number for all of the versions with that same customer number. So it's a slightly more expensive read query, but actually those parts of our system, they're on the database anyway. They're not actually, don't need to be that fast. So it doesn't seem to cost us all that much. Just a slightly more expensive query for a lookup by ID doesn't seem to hurt us very much. So that's the simplest way we've found. There's other approaches as well. You can use like secondary tables to point at this is the current record as well. But then you are back into actually having to do some update somewhere, and your ability to cache starts to go away a little bit. So we're sticking with the version numbers. Seems to be working for what we're doing. We haven't run into any performance issues with it so far. But it doesn't get hit anywhere near as hard as the sort of problems we're trying to deal with this time series data.
Okay, any more for any more? We have got a few minutes. If there's no more questions, so we have ended just a few minutes early, but that's cool. That means we'll get a jump start on the lunch. Remember to leave some for the folks in the next room. We're back in here at 1:45 with Josh Robb talking about connaissance and Sarah Hui talking about JavaScript.